Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syazani bin Shah. I'm from BEI. So for my PSM title, which is Grid-Connected A Single Microgrid with protection using Differential Relay. So I will show you my poster presentation. So before we go through the introduction, so before I want to continue to this kind of project, my previous research on the Sarawak, which is focused on the rural area. So Sarawak has installed a single microgrid that connected to a network distributed energy, which is solar and wind energy. So the place is on the rural area. So what happens when there is a natural disaster or any disturbance held at the grid utility at Padawan, which is around the line of the Padawan grid utility. The grid supply will be disconnected and the distributed generators which connected with the load in the disconnected section will continue to supply loads in Padawan. So the situation is easily can be taught as changing mode of grid mode to the ascended mode for microgrid. So when there is a changes of mode in microgrid, so there will be some risk happen for protection line. There will be need a suitable modifying protection. So mostly on this project is certainly focusing on the the changes of current that make risk on the safety of protection in the microgrid. So for the objective for my project is to model a single microgrid connected with distributed sources using PSK for Kampung Semadang grid system. So secondly, we want to perform fault analysis based on the existing current at protection system and choose the suitable specification of differential relay. So thirdly, to observe the system reliability of single microgrid with differential relay. So to achieve this objective, so we must to firstly modeling a single microgrid connected between the main utility and the distributed energy involving the solar and the wind energy that will be on the load that suitable at Kampung Semadang using PSK simulator. So secondly, we must do the analysis on the operation of the protection system when there is an internal and external fault happen around the system based on the existing current during the exchange of mode in microgrid. So thirdly, to observe the system reliability in waveform, current, existing and others. So for the methodology for my project, well, firstly, we already identified the problem, and secondly, we will study on previous case and research, which is the place on my scope is on the rural area at Sarawak, and we'll be collecting the data and information. So for this semester, we already designed and make modeling of the microgrid and simulate in ascending mode. So when we have already simulate in ascending mode, we will make a fault happen at the line based on the existing current at the protection system. So when we make the fault analysis based differential relay selected, so when there is so we will observe the system reliability of the microgrid. So when there is a disturbance happen on the line, so we will be observed on the protection system will be the breaker. Is it there will be an error or not? So from based on my dual differential relay, so for you will be show the dual differential relay on my simulation. So this is the setting that have been done based on the, as you can see, this is the formula and algorithm that will be need to be applied to succeed to follow up the characteristic of dual slope characteristic of the differential relay. So as you can see, we got the IS1, we got the K1 and K2, and this one is IS2. So based on the graph and the result that happened in my simulation, there will be internal and external cases. So on the left graph is about the internal case, the internal fault happened, and this is the result of the I differential and I bias. So on the right side is the external fault result that shown on the graph. So basically the basic engineering law that we use to understand this system is by using the Kirchhoff law. When there is the current flows in approximately same with the current flow in and out the breaker. So basically the current in Kirchhoff law, we know that the law is talking about when there is current in and the current out will be the same. So the current that throughout the protection relay must be the same which out from the differential relay. So from my system, the value of current that through the protection relay is 0.05 ampere. So when there is an internal fault happen, so at the beginning current is normally a constant operate on 0.05 without any disturbance and changes of current value occur. As it reached the fault time, so on my system I have already setting the fault time, which you can see on the graph is at the value of 2. So when there is disturbance, the I differential and I bias will begin to change and increase. So the disturbance also create noise on the power supply. So when there is a changes of current happen on the line, so there will be triggering on the breaker to be cut off on the line. So when there is a cut off on the breaker, so will be a current drop, power drop on the load. So everything will be shown on the simulation. So based on the dual slope differential relay setting, as the I differential, which is the setting will be set on 0.5, reach to the value of 0.5. So as the graph on the dual slope, the setting has been setting up the value of IS1 that will be start to be triggered on the circuit breaker is 0.5. So the breaker will be giving pulse to the breaker to be tripped. So starting the IS1 0.5, so the breaker will be start to trigger to be tripped. So the relay responds correctly in the direction of internal fault where in the operating area of fault. So from the formula of algorithm, there will be case 1 and case 2. So from the case 1 is shown as the region on the K1 graph and below. So for the case 2, I bias equal to greater than IS2 is referring to the restraint region. So basically the trip region will be on the case 1. So the case 2 will be when there is current is when there is a disturbance happen. So in the case 2, when there is a disturbance happen, the formula will go through this the system will go through this formula and will be transmit into the graph. So on the case of 2 is the restraint region. So in this area the breaker will be giving no pulse to the breaker, so the breaker will be there is no tripping happen. So by the result throughout the simulation, the adjustment on the setting of the relay is important by finding the best I bias and I differential relay setting to optimize the system within any disturbance occur either internal and external fault. So I have already made a calculation on to prove that the graph is the dual differential relay setting is already been correct to maintain the system to work correctly. So from the case 1, I got when during I bias is less than IS2. So I already replaced the numbers of data that I have already collect. So IS2 I have setting for 0.2. So the I bias is 0.05 ampere. So definitely when there is a current during I bias is less than IS2. So it's a case when there is a breaker tripping. So in this case, when I differential is got to 0.51 ampere, so when the formula has been calculated and transmit to the graph, so in this case the breaker will giving pulse to be tripped. So in this case, when I bias is greater than IS2, so this is during this case that referring to graph which is be the return region. So as we already replaced the calculation with data that been collected, and we achieved to be got the value is 0.36, which is on the restraining region, which is not already achieved the tripping region. So basically we have been proven from the simulation with the calculation that the value that we have been setting on the dual differential relay has been proved that the system is flexibility to be used. So in our on the next video, we'll be go through about the simulation that happened and we'll show you the result from the simulation. So hope you can enjoy it. So Assalamualaikum warahmatullahi wabarakatuh. So before we start our simulation on microgrid that using protection of differential protection. So I will present it the tools that we use to make this modeling. So firstly, the microgrid is consists of 3 distributed generator that there will be wind generator, the FIG, another wind generator on the other side of the line, and there will be this solar power. All 3 distributed generator is connected to the 0.6 kV bus, and this is the HV network, the main utility. So before we running, so this is the line of the microgrid that will be in the grid and the extended mode. So this is the things that will change to the extended mode. So this is our load. So when there is a disturbance happen around this line, so the changes will be around this area. So for now the load is connect to the main utility. So when there is a disturbance around this area, so there will be a cut off on this part, because we have the circuit breaker in this 2 part. So this is the disturbance that will be happen in here, which is the internal fault. So when there is a fault happen in this area, the circuit breaker will be cut off, and there will be a drop on the power that can supply to this load, and this area will be the extended mode. So for this part is about the graph that will be shown the result. So this is the I differential and the I bias. So this one will be on the green and blue one. So this one is the breaker status that will show the status of the breaker is on or off. So this one is the active and reactive power that goes to the load, and this one is the power that from the wind generator that produce. So this part is about the combination of dual differential relay that will be giving the pulse to the breaker status. So from here is there will be the current that goes to the slope, the dual slope. So this is the setting of the dual slope. So this is the differential current that we set up on 0.5. There will be the point of first, that if you're referring to the graph on the poster, based on the formula on the poster, this will be the RS1. So this one is the lower percentage bias setting, which is 0.2, will be the K1 slope. So this one is bias current threshold setting, which is 1. So this one is the higher percentage bias setting, will be the second slope, will be the K2. So the relay will be hold time for 4 milliseconds. So the graph will be seeing the holding time of the relay. So okay. So the breaker can be changed to the manual and auto mode. So as there is disturbance, can change to auto. So for now we'll be operating on auto. So with that, we will start to run the simulation. So for this case, it's about the fault in the internal fault of the microgrid. So we'll be running. So the current is start to operate. So as you can see here, the color of the current that disappear, that display is the I bias. So the color is, there is no color for the blue, which I blue is about the I bias. So I bias is, if we learn about the Kirchhoff law, which is current that came in and the current that out is equal to 0. So for now, this is the I bias is currently on I operate current, so there is no current that will be dissipated in this area. So rely on the formula that stated on the poster. So the current will be the disturbance will be triggered on the on the time of 2 that set up on this fault time. So as you can see in the breaker status, there will be no trigger of pulse given that sense from this protection system relay. So the load is currently receive power from the generator. So this is the power load from the generator, is smoothly run with no disturbance. So currently we'll be waiting for the current to be arrive at the disturbance time of fault time. So basically the current is operating is not in normal operation, which is the current from the current that in is constantly throughout the protection relay with the same current which out. So there is no changes of current in the that go through the line. So another few seconds that will goes to the internal case of fault. So you can see when there is received at this setting of the fault time, so the current is currently changed when there is a disturbance around the internal fault. So as you can see, the I differential current is of the current is changed and increased. So from the differential dual slope, the current has been overcome from keep increasing. So based on the formula that will setting up that based on the dual slope differential relay, that based on the algorithm of the formula that you can see on the poster, so the current is already been overcome. So when there is any disturbance happen on the internal area of the microgrid, so the current, if there is changes of current that comes in and out of the protection relay, so there will be no the system will be flexibility will be if there is any disturbance happen around the microgrid. And so as you can see on the active on the power, so as you can see, when there is a disturbance around the line, so the power will be dropped with the same that which the breaker, as the breaker is open on this pulse, so it means that the breaker sense the dual stroke to be triggered as there is a disturbance. So the pulse is shown as the breaker is currently be open. So when the breaker is open, so there will be a change up of mode. As there is a change up of mode from the grid and to the ascending mode, so there will be drop of power happen to the load. So that is the explanation for the internal cases. So current situation is about the external fault. So for showing the external fault graph, what is happened when there is a external fault outside the microgrid line. So I've changed the fault to be made outside of the internal part. There will be I just put it at the 0.6 k bars on this area, so the disturbance will be happen at this area. So what will happen to the current on the I differential and I bias? It will be the same on the I operate current. So when there is a disturbance happen at the external, so what will be happen at the breaker if there is a sense of fault? If as there is a breaker, as there is a sense of pulse to be sent to the breaker, if there is a disturbance happen at the fault of time of 2, so we'll be waiting for the disturbance to be happen at the default time. So as you can see in this area, there will be no I differential that occur on the graph. As you can see, the slope is happen. If you can see on the graph, the current is currently happen on the other side of the case loop, which is the I bias on the returning region. So there will be no pulse will be given to the breaker. So on this graph there will be no pulse will be given to the breaker, so the breaker there will be no open and cut off on the breaker. So everything is currently will be depending on the graph. So that's all.